As far as I know, Jack needs
I'm running on.
to give Subway his money.
At least I'll stay awake though.
There you go. There's that, because now you're hungry.
Sorry.
All right. See? There's that one.
You'll see why I moved it.
So everybody had a good summer?
Yeah.
Yes, for the most part. Good.
Good.
Why is that not? Do you think? I don't know. Okay, good. I'm glad. I'm glad. So we're going to go through today's lesson and y'all can munch away. Those of you who are new and don't know how this works, you get to munch away during class, as long as you don't fall asleep. What happens if you fall asleep?
Get shot with a Nerf
You
gun.
get shot with a Nerf gun
By you and
and hits the person behind you, because this Nerf gun does not aim well.
So if
I
you're-
actually aim fairly well. The Nerf gun does not. I blame it on the gun.
if you're not asleep.
And it's a good one too. It's a 6-shot. It's called the Disruptor. So like it's,
It's really.
My cousin has.
yeah, pretty good. And I can put my name and my initials on all the darts, so that no one takes them. So, you know, this legitimately. All right, so some of this first lesson is going over a little bit of what you guys already went over in your pre-lesson. And if you've been here before, some of it is repeat, but it's important. So it's stuff that we have to make sure we cover at the beginning of every year. And then we'll move into our newer stuff. And the newer stuff, this year, Earth Science. So I told, there goes my water. Hello. I grab me some paper towels, just a stack of them. I just knocked that over. It's no biggie. So if you're new or you missed the grilling show, I was talking about, I'm gonna need more than that. I was talking about the 4 sciences that I do, and of the 4, I think this one is probably a little, I hate to use the word easier, but concept-wise, it can be a bit easier than some of the others. And so this is a good one to start with if you're new. Yeah, can you just take care of that for me while I get it? Okay, so it's a good one to start with if you're new. And physical, which is next year, is also a little lighter. Like chem's pretty heavy, right? Those of you who've done chem with me, it's pretty heavy. It's a lot of stuff in chem. I'm gonna see if I can make my clicker work. So we're gonna talk again, what is science? We're gonna go over some of this again because it's important, like I said. Is it gonna go? You gonna do your thing?
You refill your water now?
No, it's all right. I think so. Let's see if I can make this sucker do its thing. It was picky earlier today and didn't want to. There we go. Okay, maybe it'll do it. So science is a system of knowledge and a method you use to find knowledge. So it often begins with blank and ends with blank. Now, those of you who are new, I didn't mention this in the grilling show because this is a surprise. See my coins? Yeah. Did you notice the antique bubblegum machine at the front? Okay, so I have the coins here, and if you answer questions and participate, I'll start a little stack for you. And you can take them on your way out. It doesn't matter if it's penny or quarter, the machine takes everything. So anyway, just for fun. So does anybody know what those 2 blanks might be? Alex?
Both of them are question.
Both of them are question, he says. All right, so that's the other thing I'll tell you. If you get 3 right, then we have to let some other people answer first before you answer. So you're close. So what we have is, you want to click for me? Do your thing. Fine, don't, I'll stand here. So science often begins with, question is what I would think is a good one, but your book answer was, oh gosh, I have to put this in for it to stop being ridiculous. I don't know why. I tried this thing and it doesn't love me. Oops, wrong way. Okay. So curiosity, and it ends with discovery. You could say it begins with questions and then ends with answers, but I think discovery is probably a better word than answer, because, you know, the point of science is to really look into stuff and kind of learn as you go. Yeah.
It also sounds cooler.
It does sound cooler. So what do we define as the use of knowledge to solve practical problems?
Technology.
Okay, Alex gets technology. So there's one. All right, so I saw you, Chloe. Chloe's getting in here. All right, stick this guy back up. All right, that's right. So you guys probably think of technology very often as like computers, cell phones, anything that has been basically created or invented that is for solving a problem. Somebody used the knowledge they had to build something to solve a problem. That's technology. So a shoelace is technology. A fork is technology. The lid Alex just put on his noodles is technology. Alex loves noodles. That is technology. It's all very, very good. So science and technology are interdependent. Advances in one lead to advances in another, and that makes perfect sense, right? All right, so we have our branches of science. So this was in your pre-lesson. You've probably seen this before. So you got your formal sciences, and that's stuff that's math, logic, stat. And then you have these other guys over here. What do you think, James?
Natural.
Natural. No, not natural, because that's there in the middle. What's this one here, Bailey? No, Alex.
Social.
Social sciences. Alex is on 2. All right, those are your social sciences. These study people, societies. So things like anthropology, economics, geography, political science, psychology, sociology. What's anthropology? Do you know? Do you know, Bailey? I mean, Piper? I did it again. Piper? Sorry. Y'all look alike to me. Anyway,
Helping people and stuff.
not quite. Do you know?
Isn't that nice? No.
No.
Close.
I know your.
I realize, okay.
Of what?
Different cultures.
Yeah, okay, so it's sort of the study of culture, it's the study of like historical people. And so you may hear of like a forensic anthropologist, and that's a little different. Those people tend to study, like a lot of them will study skeletons, bones, everything from mummies to crime victims, all that kind of stuff. They're very helpful. So then we get our natural sciences. That was what James was saying. So they're divided into 2 main groups. You got your life sciences and then your physical sciences. So this year we're doing earth science, and it is a physical science. So we've got one that we say is the study of nature and the properties of matter and energy. Piper? Okay.
Maybe biology or science. Like
No, not those. Jack.
Is it chemistry?
Nope. Bailey.
biology.
No. Oh, wait.
Oh,
Oh, yeah, he got it too fast. All right, physics. Oh, yeah, physics is what we're talking about. So matter and energy, there's your clue, physics. All right, so this next one is celestial objects, space, and the physical universe. Liam,
astronomy.
astronomy, you got it right. Okay, I'm gonna give you a little helpful hint for life. When you go to college and you have to take a class. All right, so Liam, this is your path. Okay, if you're one of those people who doesn't want to major in science and you have to take a science, a lot of people say, "Oh, take astronomy. That's easy. I'll just go memorize some constellations." It's not. That's a joke. That that's a lie. I know so many people who are like, "Oh, they'll do the telescope. I'll take that." There's a lot in there. It can be a really challenging class, but it's a really fun class. So don't let it dupe you. All right. So what's the study and identification of substances which matter is composed? Jack.
Chemistry.
That's chemistry, right? All right. Who's done chemistry with me? There you go. All right. That's a good one. Chemistry is a good one. All right, Jack, keep an eye on your pile. It's there. And lastly, the study of physical constitution of Earth and the atmosphere. Drew.
Aerospace?
Nope.
Arrow.
Bailey. Earth science. That's where we are this year. All right. Yes, James.
Point that is anything under life.
No, because there's only, I mean, you could put a million things under there. So since we're looking at, good point though, but since we're doing a physical science this year, we put our information there just to kind of clear it up. But there's a ton of stuff that could be. All right, so these are the kind of things you want to, this is our little engrave for eternity. Keep this in your head, right? This comes up again and again. It shows up on exams. So if you see this little guy come up, this is reminding you to like etch it on your brain, right? All right, so if we're doing physical science, although we're doing a type of physical science in general has some very big ideas. Anybody want to take a guess? This one is the little box is in the wrong space. It is forces in motion. I don't know why, but that box got moved and the answer's been given. So, oh well. And you see why I chose forces? What's this one right here?
That's Space Force.
That's Space Force. What's this one?
Army.
Army,
Navy.
Navy.
Coast
Ooh,
Guard.
Coast Guard,
Air Force.
Air Force and
Marines.
Marines, right? So I did armed forces to kind of clue you in. And then there's an arrow for motion. So how about this one? What do you think this represents?
Space travel and space exploration stuff.
You got about half right. I'll go for that there, Piper. That's space and time. Okay, this is your pile, Piper. All right, space and time. And how about this one? Anybody want to take a guess what that might represent? Liam?
Atomic particles.
No, good guess. All right, this one is going to be, oops, sorry, I went to the wrong way. That's energy, batteries, duh. All right, so this one is going to be matter and change. What's this symbol right here?
Delta.
Delta. What's delta mean?
Change.
Change. All right, so you'll see that a lot more. So how are we going to define space? So here's one way you could define space. Space is a hard thing to define, right? So basically it's like this continuous area or this expanse in which free, available, unoccupied, kind of hard to define space, right? It's so ambiguous. And then you got dimensions of height, depth, and width. Okay, that's helpful. You can understand that, right? length, width, height, that kind of thing, in which matter exists and moves. So that gives you some idea of the dimensions, matter within it. That is space. It's a really ambiguous thing to define. How about time? Anybody want to try and define time? Liam?
Man-made.
Man-made, okay. Anybody else? So time's not man-made, maybe how we measure it is, but time is measured or measurable, and it's the period in which an action or a process takes place. So I threw the ball and that action occurred over time. You can measure that time with a stopwatch, right? And this other part's a little, woo-hoo, it's wordy, the non-spatial continuum that is measured in terms of events which succeed one another. So September turns into October, October turns into November. So events and things go after one another within a spectrum of time. All right, forces. This one's easy to define. What's a force? Do you know?
Something applying
You're close.
applying work, or
Plus.
doing work on another.
There's a real short one when we do physical science next year. It's a push or a pull on an object, basically. So force is a push or a pull on an object, which is matter. And matter, we'll define that in a minute, but there's also a real easy one for that too. And the reason I highlighted these words is you can see how these things are interconnected. So there's lots of big ways to define force, but the easy way is it's a push or a pull on an object. So motion. This one is where you have to start thinking about matter and time, and here's why. So it is the change, so here's your delta, it's the change with time of the position or orientation of a body. That doesn't mean like a person, it's anything, an object, right? So think about that. If you had a ball on the floor and it was right here and it rolled to right there, the matter changed position over a direct period of time. That's motion. Does that make sense? But you see, time, matter, space, all these things are involved because the position was changed in space. So then change. Okay, so this is, matter. Matter is easily defined as what? It's the bottom one. Anything that has mass and takes up space. Okay, so here you have space again. And this is basically together with energy, it's going to matter and energy form basically the basis for all objective phenomena. So anything you can witness and observe. So if I dropped a ball, it's made of matter, some kind of energy had, to release it, and then some kind of energy has to move it. Okay. Change, how we're defining change. All right, so yes.
One form of matter
Mhm.
changing into another form of matter.
Yep, sometimes that's it. So in chemistry, that can be, this is your cut, right? That in chemistry, that can definitely be it. You have one form of matter that changes to another form of matter. You can also, that would be a change in what? State of matter. So then you've also got transition from one theory to another theory, process in which one or more substances are altered. Don't have to be changed into another. Maybe they're just altered. They may be in the same state of matter, but maybe they're a different kind of matter, right? And then how do we define energy? Anybody besides Alex want to go? Alex, what are you going to say?
The potential to do work.
That's what it is. Okay, so energy is the capacity or the potential to do work. And the batteries are really good example to use. So if I put, I'm going to drop the AC a little bit. So if I put say I have a battery operated toy and I put the toy on the table and then I put a battery on the table. The toy isn't going to work until the battery is placed in it, right? The battery isn't doing any work, right? And we can get into defining work and we'll do a lot of that when we do physical science, but the battery isn't doing anything. It's just sitting there, but it has the potential to do work. So it has energy. Like when you are eating right now, that food has calories in it. And those calories are what you're going to burn, right? When you use energy within your body to move your muscles and go for all of your other biological processes. So that food itself has the potential to do energy, right? So the capacity to do work. That's what that is. All right. So ideas in earth science in particular. So systems. If you go into engineering, and some of you may go into engineering because I know you're people, maybe you're like primed for that. If you go into engineering, you're going to talk a lot about systems. Engineers are all about systems, right? Engineer in the kitchen. Would you agree? You're not even listening.
Yeah.
Systems. Yes. Okay. So Earth is a system within a system that contains other systems. So think about that for a minute. You have a universe, that's a system. You have a solar system. The Earth is within the solar system.
Galaxy is the system of
The
us.
galaxy, yeah. So you have your universe, your galaxy, your solar system, right? And then you have your Earth. And within your Earth, you have your biosphere, and there are systems within that. You have your hydrosphere, and there are systems within that. Your body is full of systems. So it's a system within systems full of other systems. Right. So that's kind of like, I always think of the end of the first Men in Black movie when they look at the little marble on the cat. You know what I'm talking about? When the cat's collar, like a little marble, and there's like a whole universe in there. So it's a universe within a universe. All right. So then energy. So the flow of energy is going to drive the cycling of matter. So by cycling of matter, we just have to consider the fact that there's some matter that's going to sit relatively unchanged for a long, long time. There's some matter we're going to change. For example, there's a nickel right here. Nickels are made of nickel, right? And the nickel's got to be mined out of the ground from rocks, right? And then it's got to be melted and stamped into a coin. And if this coin got super damaged and it made its way back to the US Mint, what would they do with it? Melt down and stamp it into a coin again, right? So that's a cycle that is driven by humans. But you've got leaves on the tree and they fall to the ground and they become detritus and they rot and all their nutrients go back into the ground, right? And then they get sucked up through the tree's roots. So again, that's cycling around and around. So energy is going to cycle, and that energy is what the chemicals from the ground are what the tree is going to use for photosynthesis. So that's where the energy comes in. So energy is going to drive the cycling of matter. Okay, now life and environment, including human life, influences and is influenced by the environment. Somebody tell me a way we influence the environment. Bailey.
Deforestation.
Deforestation, that's a good one. All right, there's your file. Deforestation, yes, we do it that way. And around here, we've had way too much of that, right? Everybody who lives in Forsyth County is like, man, they're putting a house everywhere. Tell me a way the environment influences us. Piper.
Like currents in the ocean depend on how people travel through the ocean.
There you go. It's a really good example. This was your, right? Yeah, so those are good examples. All right, so keep those in mind as we work through this year. So this is a really good one to think about. The unchanging drives change. So physical and chemical principles are unchanging and drive both gradual and rapid changes in the Earth systems. So think of a physical property that is unchanging. And how does it drive change here on Earth? Anybody think of an example? Jack, you're thinking? You're not sure?
I guess it does.
Go ahead, what?
I was just thinking like, I don't know, like a mountain
Mm-hmm.
is there, right?
Yeah.
And there's snow, and then the snow evaporates and becomes water. And
Right.
It creates streams.
Right. That's a great, or the snow will melt. So what's the physical property there that's causing the? Yeah, well, it has to do with the fact that water is always going to melt. It's going to be liquid. Water's going to be in liquid form anywhere above what temperature? You know.
32 degrees Fahrenheit, 0 Celsius.
Celsius is the one we're looking for. Yeah, 0 Celsius. So that is an unchanging principle, right? At a certain pressure, at a certain, always the pressure, when we get to physical science, you'll learn that the pressure can change what temperature that water will shift. But at a given pressure, however many atmospheres, water is going to melt at this temperature from ice to water, and that's going to cause a stream. Okay, so that's a good physical one. What's a chemical principle that doesn't change, that drives both gradual and rapid? Can we think of a chemical principle that doesn't change that affects the Earth? Think of one. A chemical principle. This one's a little trickier.
Could you say it again?
Think of a chemical principle that's an unchanging principle that can drive change on the planet. James? That's a great example. Good, James. All right. I think that was, where were you? Were you?
I don't have-
And there you go. Okay, that's you. Yeah, photosynthesis. So wait, expand on that.
It's always gonna happen,
Mm-hmm.
like it's.
So it's going to happen if light hits the leaf, because it's just going to be. Yeah, and then we grow trees and we get food. Very good.
That was good.
Perfect example. That's a challenging one. All right, so modeling and mapping. We're going to do a lot of modeling and mapping in our science. When we're talking about our solar system, we're talking about stuff that is way far away, it's going to be really helpful to model it. And when we're talking about the Earth and how things are situated and where they are, it's really helpful to map it, okay? Modeling is really, really good, especially when you're talking about stuff that is either really tiny or really big, because it's hard to conceptualize. If you've done chem with me, you know that like modeling an atom is pretty much so that you can see it is almost impossible, right? Because we do those nice little Bohr models where you've probably seen them where it's like circles and then circles. And that gives you a good idea of what's there, but it doesn't give you a good concept of how it actually moves because those electrons are like a cloud. They're just kind of going all around in different directions. They don't act like the solar system. So modeling and mapping are really big in this one. So science is awesome. Here's your perspective, things to keep in mind. So science is a process and a body of knowledge. There is a process. And then because it's a process, science changes. So in the earlier class, I gave the example of COVID at the beginning because everybody lived this, so you all know it. But you probably remember there was a period of time where like the CDC, which is our, Center for Disease Control, it's sort of our go-to body for directions on what to do in medical situations, right? What should we do? One day they would be like, wearing masks is great. And then the next day they were like, well, these people don't need them. And then the next day they were like, well, nobody needs them. And then they were like, everybody needs them. Do y'all remember this? And the public got frustrated. And a lot of the public lost faith in the CDC's recommendations because they were like, they don't know what they're doing. They change their mind every day. But actually they're doing science because as they got more data, they were able to come up with more, provide more information for us based on the data they collected. And if it wasn't changing, I would be worried. If they said day one, we're going to do this, and then they never changed it, that would concern me because it's like, are you guys even looking at this anymore? Right? So it's a process, and that's part of the process. And then the body of knowledge is everything you learn within it. Be skeptical. So that means don't just take everything at face value. If I say the sky is purple, don't believe me. Look at it yourself. If you're in a padded room and you're locked in and you can't see the sky, go online and do some research. What color is the sky? Is it really purple? Right? And we're going to do, like I said, this year, we're going to do 2 documentaries that are total counterpoint to one another. So always be skeptical. So ask questions. If you don't ask questions, you never get answers, right? And believe in the process. Now, what this doesn't mean that you're not going to be skeptical. Be skeptical of data sources. Be skeptical of who is presenting the data. Be skeptical of how experiments or research was done. Look it up yourself. But the process, on the other hand, you can have faith in, because if it's done correctly, if you're doing science correctly, you're limiting your variables, then your results are going to be pretty consistently valuable or correct or affirmed. Something to consider when you're talking about believing in the process and what the process is sample size. So if we go back to the COVID thing, all right, say they had 10 people and they told these 10 people to wear masks everywhere they went for the next week and nobody caught COVID. Okay, and then they came back and said, wear masks, you'll never catch COVID. 10 people is not enough for a survey like that. You need 1,000 people or 100 people. So that's sample size. So sometimes you'll see something in the news. This is a great example. You'll see a news thing pop up on your phone or whatever, and it'll say like, bacon causes baldness in women. And you're like, oh my gosh. All right, look at the study. And if they studied 4 people, don't go, just, that is nothing. That is not valuable information. That's not enough because, and here's why, here's a way to make it clear. Say you had a town and there were 50,000 people in this town, okay? And you took all of their ages and you averaged them up, you'd probably get something in the 40s, usually 43, somewhere around there. That's usually like an average, okay? And say somebody in that town had sextuplets. Oh my gosh, all right. Is that 43 gonna shift a lot? Probably not. Now say you had 50 people in a town and your average age was 43, and then somebody in the town had sextuplets, 6 babies. Is that going to shift the average? Yeah, because there's not enough people to get a true median sort of, in that case, like it wouldn't really display what the town's makeup is, because babies born like a day later. It'll give you an average, but it shows you how that sample size can shift your answer hugely, right? So that's why you need a big sample size when you're doing studies. So how do we do a scientific approach? What's that mean? So here, what do we call an organized plan for gathering information and communicating information? Caitlin.
Hypothesis.
Almost. Ha, Alex,
Scientific
you've
method.
got your 3 already. Yep, scientific method. That's what we're talking about here. So the goal is going to be to solve a problem. So today you formed a hypothesis, but then you used scientific method, hopefully somewhat scientific, to try and figure out what was going on in these boxes, right? But you have to use scientific method because you got to limit your variables. You wouldn't be thinking like, oh, there may be a car in this box, right? Like that's ridiculous, right? So what do you call it when you have information that you're obtaining through your senses, Drew?
Observation.
Observation. I think this is you? Oh no, observation. All right. So what are your senses?
Sight, taste, touch, audio,
Hearing and this one
scent.
and smell. Those are the 5 you usually hear. There's a 6th one that they don't include very often. Oh boy, James. Yep. What's the word for it?
Probably scent.
Proprioception. All right. Proprioception. Yep. Is where your body is in space. Okay. So you know that you're sitting right now. And even if you closed your eyes, you would still know that you're sitting. And if you stood up and turned in a circle, even with your eyes closed, you would know you're doing that, right? That's proprioception. Pilots have great proprioception. They're able to maneuver through space, wide open space, and move their machine, their plane, up, down, right, left. They know where they are. And I was talking earlier, gymnasts have good proprioception. So we've got a couple gymnasts in this group. Gymnasts have great proprioception. And it was a story that was a great example. There were 2 gymnasts who were rock climbing together. These guys were like in their 20s and they'd done gymnastics through high school together. And then they just kind of played around. They weren't doing like college competition level stuff, but they're still really fit, buff guys. And they were climbing a rock wall. Something happened and they fell. And they fell like, it was something crazy, like 60 feet. I mean, it was ridiculous. And they weren't really injured, not majorly injured, because they knew where their body was in space as they fell. And they were able to manipulate their body into a position that would cause less injury when they landed. And all of that was just built into their brain because they trained it.
Sports players have to have great perception.
Yep. Especially with stuff like swimming. Or what's another one that would be good for proprioception? We really know where your body is. Dance is a great one. Yeah, that kind of stuff. You really got to know. All right. So what is the proposed answer to a question? Caitlin, you know this. What's the proposed answer to a question? You said it a second ago. There you go. So another way to, here you are over here. Another way to define hypothesis is it's a question, an idea that can be tested. And we talk about what makes a good hypothesis versus what makes a not good hypothesis. A good hypothesis it has to be testable and repeatable. And when it's repeated, the results either need to be affirmed or rejected every time, right? That's how they work. So you have this idea of scientific method as an ongoing process, but the thing to remember is it's not going to be like a one-way thing. It's not a point A to point B. You may change the process somewhere in the middle based on the data you're collecting and the observations you're making. And you go, we had to shift. But you still have to keep things like variables in mind. So, like I said, you don't do the point A to point B. Come on, animation. You are not working for me today. There we go. And that's something you're going to want to commit to memory. So who came up with this idea of scientific method? Well, it goes way back. We're talking like way back, Aristotle way back. All right. Way back, so that we only have statues of him carved out of marble. We don't even have paintings way back. All right. So he had the idea about cycles and how you could deduce things from what you're seeing and how that could continue advancing our general knowledge base and education of people. And then we have this guy who we don't include very often, but we really should. I'm going to try and say it. I looked it up, but it was hours ago. It's like Haytham. Anyway, this guy was in Iraq, Egypt, Arabia, and this guy really had a very specific method. And he had, his was ours is more flexible today because we found that it kind of needs to be, but his method was very specific. And so he really started the more kind of concrete, structured process, which is good. It's important to do that. And then we have Sir Francis Bacon, who, as I said earlier today, he looks very judgy to me, but he was a very good scientist. He's very well known. We're all thankful for Sir Francis Bacon. He just looks like he's going to go, you see, doesn't he? That big old, those Elizabethan collars, man, they look super duper uncomfortable. I mean, I had to wear them in a choir performance once. I can't imagine wearing it every day. An hour is enough. And then lastly, our big person we can throw in this basket is Galileo. So you guys probably heard of Galileo. I mean, if nothing else, his name's in a Queen song, good. Yeah,
He like invented the telescope.
yeah, he had the first refracting telescope, right? So he is best known probably for telescopes. And then what was it that happened with him? Do you guys know? It was a big deal. Do you know, Liam?
He proved that the Earth wasn't the center of the solar system.
Yeah, and what was the response to that?
Not great.
Yeah, do you know? Yeah, it was not great. And why was it not great? Because general public didn't want to hear that. The church didn't want to hear that. And it went against teachings at the time. So he kind of got ostracized for some of that. And it was not super for him. Yeah.
He was also put under house arrest, if I remember correctly.
Yeah.
Was he the one that got executed?
I don't think so. I'm pretty sure he did not.
I think he was under house.
He was,
arrest.
yeah, he was. And interestingly, I haven't read it and I mean to read it, but there's a book called, I think it's called Galileo's Daughter. And his daughter was a nun. And is it Black Hawk?
Yeah.
Yeah, cool. They come past here when they're doing their flights. It's a low one. I can't say it yet, but
Awesome.
Drew got to fly in one this summer and we're all still jealous. So, yeah, so anyway, it's a book of notes, letters between him and his daughter. His daughter was a nun. And this was at the point when the church was very unhappy with him because he had basically gone against their teachings and said, no, the sun is the center, not the earth. And they were like, it's not what we said. And so apparently the conversations are really, really interesting. So I'd like to read it someday. So if you're interested in cool, kind of historically based books, apparently it's a really good one. So we have our variables. Okay, this is another commit to your brain thing. So these variables, we have first one, it's the one that's manipulated by the experimenter and it can cause a change. So we call it what I change. What is it, Jack?
Independent.
Yeah, it's independent. And sometimes people call it the manipulated variable. I don't like that one, but it does make sense because it's what you are manipulating. I came up when it was always called independent because it's on its own, right? You're putting it in and nothing is happening to it. It's what's causing change. It's what you change in an experiment. So the next one is changed by what you change. So we call it what you observe. Piper.
Dependent.
There's your dependent variable. It depends on what your independent variable does. And sometimes we call it responding. And that makes sense because it responds to what was manipulated. And what's this last one, Liam?
Control.
Your control. All right. I think you're here. All right. So your control. All right. So this is your standard for comparison. So it's what you keep the same. So we had a great example in our first class. One of our Cal said he gets car sick. All right. And so I said, all right, so let's say your hypothesis was, what color is the interior of your mom's car? And he said black. I said, all right. So say your hypothesis is that when you sit with black all around you, you get sick. And I said, so how could you test it? That's going to be your independent variable. So what things could you, in this case, it's black. So could you do? So what were some suggestions you think?
You could just like sit in a dark room.
You could do that. What else?
Dye the inside of the car.
That's going to be
violently orange.
expensive, Drew.
Drive a car that has a white or.
Yeah, get the different driving in a car. I said, what if I put you in my van? I said, there's some black in my van, but it's mostly tan. What if I put you in my van and you still got sick? So it's not black, right? So that's what you're changing is that color, but everything else was the same. He's still riding, he's still in the back seat. If you want to be really specific, it would have to be like same time of day, same car, same seat, same everything, right? So
Just different color.
yeah, change the color only. And that way he would know, well, it's not that. So we came up with some other things he could do to try and figure it out too. So let's say I hypothesize that girls are smarter than boys. I give a pop quiz on lesson 1. Most of the girls score higher than most of the boys. So I say, yay, my hypothesis is supported. Girls are smarter than boys. What's wrong with my experiment?
Sample size.
Sample size. What else is wrong with it? I did it one time. I didn't repeat it. What else? Come on, there's lots wrong with it, Drew.
I don't know what questions are on.
Yeah, it does.
Each person has a varying level of smartness. So.
Right. There's varying levels of, and who's learned what, studied what. I don't know the ratio. That's a very good point. Alex, you got another?
You don't know how good people are at a specific subject. and you're
Right.
putting them on.
Right. And how about one more from Piper?
You don't know how well their memory is if they have all of it.
Very good. Okay. Those are all good. Also, another thing to consider in an experiment like this is bias. Let's say the questions I put on the pop quiz are, 3-stranded braid can be made into a French braid by lifting from below, true or false? Who's probably more likely to get that right? Somebody who braids their hair. So if you have longer hair and you braid it, that's probably going to be something that you're better at. And you could get that question right. There are other biases I could do that would be more likely for girls to get right than boys, based on things that are more likely that girls do, know, whatever, right? It would put the boys at a disadvantage. So this is sometimes an issue when you do testing too, in general. They can put certain entire, populations at a disadvantage based on the questions that are asked. So keep that in mind, because that is absolutely ridiculous, ridiculous, ridiculous. We don't want to do that, right? We want to have a good experiment. It's ridiculous. Class is ridiculous, right? All right. So what we like to do is consider, well, let me go over draw conclusions first. So if your data doesn't support your hypothesis, you rewrite it or revise it, and you conduct a new experiment with a new hypothesis. So what we like to say in science now, we'll move on to theories. We're going to develop a theory. We have theories and we have laws. So which one of these is describing a theory? All right, Chloe.
The theory is, sustained explanations.
Okay, a well-sustained explanation of something, she says. All right. Anybody else have feedback?
I think the law is the rule or principle that always works the same way.
Okay, so let's see what we have. So your law is your rule or principle that always works the same way. I think you've got 3. And then your theory is your well-substantiated explanation. Boy, these are longer definitions. So how do we slim it down? We do this, all right? Your theory tells what happens. It explains something. It's a truth. It doesn't explain it. Sorry, it tells it. It's a truth. Your theory tells why it happens. So something to remember, because people always want to go to gravity as a great example. Okay, gravity is described as both a theory and a law. Okay, so if I have a ball and I let it go, Mitchell, oops, sorry, no, Mitchell, Liam, 2 people. Today I got those 2 confused. Okay, if I have a ball, I let it go. Where's it going to go? To the ground. Okay, if I do it again, where's it going to go? Is it ever going to go up?
No.
Is it ever going to go left or right? If I just drop it, right here where I'm standing, it's always going to go down. That's a law, right? We're going to say that's because, well, gravity, that's why it's going down. That's the law. We're going to name it gravity. Okay, but the theory behind why it's going down, what's the theory behind why it's going down? It's going down because objects are always attracted to one another. That's the theory of gravity. And if you drop a ball that's small, it's going to be attracted to the larger object. In this case, the earth, not even the floor, the earth. So everything is attracted, getting pulled towards the center of the earth. You, me, everything else. That's why when you jump, you come back down, because you're getting pulled towards the center of the earth, because you're smaller and the earth is bigger. That's the whole theory of gravity. So there's a difference between, the theory and the law of gravity, but you can explain, you can see the both, like in the idea of dropping a ball, right? All right. So Alex, you look like you have a question. You're thinking. Are you thinking? Maybe not. He looked like he was really thinking hard.
That's a great GIF on the right.
Mm-hmm. I love those. Those were great. Those were fun. I had fun
On the
finding them.
left looks like Nick Fury from the Marvel movie.
Well, that's good.
That's because it is.
Part of that it is.
Mm-hmm.
Doesn't have the eye patch on.
You're funny, Jack. It turns out it is. All right. So models. We're going to use a lot of models in this class because it's really hard to visualize the interior of the planet or the continental plates or space without models. It's just like we said before, when it comes to modeling things, it's things that are really big and things that are really small are best modeled. And other things to do are charts and graphs, and we will do them mostly in lab. We'll do some charts and graphs, and you'll learn about X and Y axis if you don't already know. And charts and graphs are pretty similar. Your graph usually has your axis, right? Your left, your X and your Y axis, and then your chart can be any of these other kinds of diagrams. And sometimes when we do a lab and we get data, we'll plug it in to Excel. We've done that before, and it spits out a chart for us or a graph for us. I don't want that. Go away. That'll help us understand better, help us visualize better what our data was. So let's talk about measurement. Measurement is important. Okay, so in science, we use these guys. It stands for Système International d'Unité. Anybody? They are Jack, Alex.
Wait,
Yeah,
metric system?
We call them SI units, but it is metric system, but SI units is just another word for it.
Yeah, I was gonna say
So you may hear that or see that somewhere. So how do we measure length, everybody together? What's the base unit? Say it, just say it.
Meter.
Meters, okay, that's how we measure length, right? How do we measure mass?
Volume?
Grams.
Grams, very good. Okay, mass is how much matter there is, remember that. How do we measure weight? No, not pounds.
Grams.
It is grams. Okay, think about it though. So
Pounds is
if I
grams.
put Jack on the moon, Jack would not lose mass, right? All of Jack is still there. We didn't take anything away from Jack. We didn't like chop off his arm or whatever. We just put Jack in space.
You'll lose
But Jack is gonna, yes, Jack would lose weight because weight is the effective gravity on mass. So if he's on the moon, he's gonna be further from the big thing, which is the Earth, and he's going to be lighter. This is why you float in space, right? Because your mass doesn't change, but the effect of gravity does on you, so your weight does change. If you tried to weigh a floating astronaut, you would have a difficult time.
But then how would grams be inaccurate?
Because it still describes, for the purposes of how you're functioning in lab, it still describes the same thing. Because we're not doing it on space, it's space. And if we were, we would talk about how many atmospheres it's in. We would say it's so and so many grams at so and so many atmospheres, and that would be how we would describe it. So area, do we know how we do that one?
Meters squared.
There you go, meters squared, very good. So then volume would be what? Meters cubed, right? Because 2D, 1, 2, is gonna be meters squared, 3D, length, width, height. So remember, area is like how many tiles go on the floor. And volume is like how many boxes can I fit in the storage unit, right? Okay, so density, how do we do density? Anybody know? You know, Alex?
Grams per meter cubed.
Ooh, look at this, close, kilogram per meter cube. Yep, I don't know why, but that's what we do. We typically go with kilogram. And should be gram, you would think, but for whatever reason, this is where we tend to go. Can't explain that one to you. And what do we use for time? There's lots of ways to break up time. Which unit do we use? Say it. Second, we use seconds, right? We don't use minutes or hours, we use seconds. And then temperature, we do Celsius, right? All right, so
Like the rest of the world.
these are our base units in the middle. And then if we divide them by 10, you're gonna get a what? It's a decimeter. Yeah, well, so this is getting smaller. You've got a decimeter is smaller than a meter,
Oh.
right? And if you multiply it by 10, you're gonna get a decameter, right? So this is basically 1/10 of a meter. This is 10 meters, right? And that's how it works. So this next one would be centi, and then what? Hecto. What are the next two? Divided by 1,000 is
Milli.
milli, multiplied by 1,000 is
Kilo.
kilo. Very good. And then they keep going, right? There are more of these in both directions, but typically we can stay within this range. So this is another one you want to get in your brain. All right, now this is how scientific notation works. If you're using a really, really, really big number or a really, really, really small number, you probably don't want to write the whole number out because it's kind of ridiculous. Like you don't want to write it was this many grams. Nobody wants to write that or even read it, or it was this many grams. Good gracious, nobody wants to read that. So what we do, and these are the other ones. See, I did the mega, giga, tera, penta, exa, right? They keep going. So if you have a big number like this, it's easier to break it down like this. This is scientific notation. Now, sometimes it'll be whole number, decimal, and some digits, and then times 10 to an exponent. But there's something I want you to notice, times 10 to an exponent. Look at the exponents. Is there a pattern with the exponents? Alex sees it. Who else sees it? So we got 1, 2, 3, 6, 9, 12, 15, 18. And then over here, we got 1, 2, 3, 6, 9, 12, 15, 18. What do you see, Piper?
Is it the amount of zeros is the thing above the 10?
Yeah, it is. But I'm asking about the exponent in particular. Like we see 1, 2, 3, 6, 9, 10, 12, 15, 18. Do we see an 11 or a 17? Like what's the pattern? Do you see it, Chloe?
After 3, it's all multiples of 3.
It's very good. After 3, it's all multiples of 3. There's a very good reason for that. This is the reason for that. How do you write a number? Like we write the number 4,000, you write it 4,000. So here's why we use multiples of 3. Because when you write it, that's where the commas go. So if you are trying to make your life easy, you use multiples of 3 because that's the way you would write the number out. So it makes sense to do it that way, right? All right, so let's talk about Earth systems now. Earth has systems and it's in a system. Yay! It's like a hall of mirrors. So what is a system? All right, so your systems, you've got logic and math, which we talked about earlier. Those are your
Formal science.
yes, thank you, formal sciences. And then you get your systems science, right? And these break down, you got your physical, your living, and you got systems within here. Animals have, like last year, we've talked about this many times, organisms are built up from the cell,
Tissue,
cell,
cell,
tissue,
organ system, organism. Very good. Those are systems right there, right? Very good. And yeah, okay. How about if you took a, man, those are harder to do. You know what I mean? So yeah, so there's lots of systems and they've got systems within social systems. For example, we have a house within a neighborhood, within a county, within a state, within a country, within a world, a continent, within a world, right? All these are systems. And you could also look at it like governmentally. We have a mayor, we have,
Within a governor,
yeah,
within,
and that's kind of just that system. And then there's another one. We have a congressman and a senator and a president. That's a whole separate system. Representative. So a system is a group of interacting or interrelated elements that act according to a set of rules from a unified whole. Okay, set of rules. When we're talking about science, these rules tend to be scientific laws, things that don't change. So a system surrounded and influenced by its environment is described by its boundaries, structure, and purpose, and expressed in its functioning. That's kind of hard to put into your brain, but basically what it's saying is the system is affected by the environment and then it affects the environment as well, right? So types of systems in science. So if we start talking about thermodynamics, this is a good way to do it. Next year, we do physical science, we will get into thermodynamics, and we'll talk about these laws. Whose laws are these? Anybody know? It's got a name, somebody's laws. Ooh, Jeff. Newton, very good. So Newton basically had 3 laws of thermodynamics. He had the first, second, and third law. And then later they developed zeroth. Why they didn't go to 4th is still, to me, I'm like, were we trying to be cute? So that's basically, when we consider the laws of thermodynamics, we can talk about the systems that we're going to use. Yeah, right.
It's practical.
Mhm.
They're like,
It
sure,
does seem like
why
it should be, right?
Just throw 0 in.
But we're gonna use these laws to talk about some systems, and this will come up. So this is stuff to kind of keep in your brain. So an open system, this is exchanging energy and matter with things within and without of the system. Great example would be like your digestive system is an open system, right? You're eating things, you have waste coming out, you're interacting with the environment by putting things into it, taking things out of it, both matter and energy. Once that digestive system turns those calories into, their heat and your body uses it, so then you're putting out energy, right? And then you have a closed system. And this is when you could only exchange energy and matter. You can only exchange energy with its surroundings, not matter. Only energy, not matter. Okay, and then another example would be your isolated system. So this is one that cannot exchange either matter or energy with its surroundings. So perfect isolated system is really not, this is more of a, I want to say it's almost like a hypothetical system. It's an ideal system, kind of like when we use the ideal gas law in chemistry. We're like, we're just going to pretend there's a gas that follows these rules. It's ideal, it's like that kind of a thing, right? So here's some, keep them in your brain. Here's some examples. All right, so good example of your open system. You got a pot of water on the stove and it's boiling. So you're exchanging both energy and matter with the air, right? So the system in the pot and the general system of your kitchen are exchanging matter because you've got water vapor leaving the pot, right? And you also have heat leaving the pot. Now, another example here of your, an example here of your closed system, a balloon. Now, this isn't a perfect example because if you've had a balloon before and you leave it for a couple days, it shrivels up because it isn't impermeable. It isn't perfectly impermeable, but it's somewhat impermeable. So if the balloon doesn't trade matter with anything outside the balloon, that's the idea, right? And if the balloon was inflated with hot air, you'd be able to feel the heat, but it can exchange the heat energy, but the air is staying in it.
That's also the reason that helium balloons can't be made from normal balloons. The helium will just escape through the
Latex,
latex.
yeah. Well, and that's the thing is, it's like, even helium balloons will deflate quickly, even if you use the good stuff, because it's not perfectly impermeable. And the same thing with regular blow it up balloons. And if you were here last year in biology, when we made the little model cells with the Ziploc, or not the Ziploc, the sandwich bags, I mean, you'd think a plastic bag, you could put water in it and carry it around, right? It would be fine. But we had iodine and starch go in, and we had iodine molecules that were passing right through that membrane because it's selectively permeable. It wasn't completely impermeable. So that's why your isolated system is really difficult to come by, because matter just doesn't always function that way. So the best example would be like a thermos. You put your hot soup inside. It doesn't exchange the heat with the environment around it. It doesn't exchange matter. Everything stays inside. You can touch the outside. It still feels cold if it's a room temperature. If it's a good thermos, those are hard to find too, right? It's well insulated. That's the idea of an isolated system, but they're very theoretical in practice. So when we talk about Earth systems, we have one system that's going to consist of the crust, mantle, inner core, outer core. You know what system this is? Anybody know? Most of these Earth systems end in the words, well, the prefix sphere, if that helps you. Check. Chloe.
Biosphere?
Nope, close though. So this one is Liam.
Atmosphere?
Nope.
Geosphere?
Geosphere. This is going to be your geosphere. This is your Earth. Anytime you see geo, it has to do with Earth, right? You may see geography.
Geology?
All right, all that stuff, geo. All right, so this is one you're going to want to keep, right, in your head. Earth's atmosphere. Look at this. So that's going to be your what? Your gases surrounding Earth. The answer is right there on this one. So, but your atmosphere has layers, and we'll learn these, right? It has layers, tiers of the atmosphere. So this is going to be your atmosphere. All right, what'd you find?
It doesn't have ozone spelled correctly.
I didn't write that. I think I wonder why that is, but you're right. That's interesting.
So no
it's
brownie
not
points, you're
points,
trying.
It's just.
It's
it
interesting.
bugged Me.
Yeah, you're right. I think I was distracted by the meteors and didn't notice. All right, so what's this one? The water on Earth.
The
Milo.
Hydrosphere?
Hydrosphere. This is our hydrosphere. Right on. So this is going to include your water cycle, obviously, that y'all probably learned when you were itty bitty people. All right, and then remember that one. And the living things, Chloe, what's that one? That's gonna be your biosphere. So make my line where you are here, somewhere in here. Y'all are gonna have to remember. I put them. I'm gonna have to make a little piece of paper or something with names on it.
Do I not get a point for?
Yeah, I got
geosphere?
I got new slots, baby.
Yeah. No, there's just put random points. All right, so moving on. All these you're gonna want to remember. So lab safety, we'll go over it briefly because we did kind of go over it when we did lab, but I want you to note these things are in your binder. We went over this deal, right? You're going to see some of these symbols sometimes in your labs when this one in particular, because I think this one's right out of your textbook. So you'll see some of these in your labs. And so as the seniors, you guys need to be really careful that you're paying attention to them so that, especially if you're team captain, so you know what precautions to take, right? You need to take precautions about, yeah. I mean, in this class, we're probably not gonna have a lot of like plant safety, but we may have sharp objects, we may have hand safety, eye protection. In a couple weeks, we are gonna do the lab. It's a crystal lab and it will involve burners. There won't be too many labs that do burners this year, but that will be one. And so you're gonna wanna be careful about safety with that. So what are some reasons for, let me see. So what are some reasons for the closed-toed shoes? Today it wouldn't matter, but in some labs it does. What do you think?
In case you drop something on them, especially if it has the chemicals.
Chemicals, yeah. What else might land on them? What have we had in here?
Glass.
Yeah. We've had glass shatter, right? We've had beakers. We've had graduated cylinders go everywhere. So,
Also like a heavy thing.
We are going to be using some heavy things like plumb bobs. You don't want those to land on your toes. What, Alex, what you got?
Acid, flaming object.
Bases?
Bait.
Yeah, any of those things.
Last animal.
Yeah, yeah. Hopefully we won't have any rabid animals. Why don't you want to eat or drink in the lab, Drew?
Chemicals mixed with other chemicals.
Mm-hmm. Yeah, you don't want to get a drop of something on your burger here, like they have this picture of this burger and this drink. I don't know who's bringing burgers to class, but duh. So we don't have lab coats. Like I said, we do have aprons. They'll be brought out to you if you need them. The one thing I think is hard for people to remember is the eye protection. Sometimes you put it on and then you pop it up on your head to get a better look at something and then you forget to bring it back down. Try to be really, really aware of it, especially if you're working with other people. If you already wear glasses, you're probably going to be good unless we're doing something like really involved. Nothing I think this year is going to prevent you from needing to wear something other than the glasses you already have. Like glasses should be fine. But if you don't have glasses, and especially if you have contacts in, like I do, you want to not get stuff splashed in your eyes because that's really, really bad. Okay, so this is a reminder that you can get 2 extra credit points for class participation. This is the Portal 2 of 2 assignment. And these are some of the ways that some people in this class have gotten 2 points extra credit. Yes.
Mine's not on there.
If yours came in last night or this morning, yours did. It's not on there.
I was supposed to send it in the day. I was
Mhm.
supposed to.
That's send it in.
Write it down.
So if it gets to me by today, you still get 2 points. By tomorrow, it's going to be down to 1 point. And by next Wednesday, there won't be any opportunity for any credit. Yeah.
Do I email it?
No, you answer. How does he do it? What's he do? How's he do it? You have to answer on the
It
video.
told me to
Mhm.
like put in the comments.
Yeah, actually, no, it wasn't Portal 2 of 2. It was the video. Sorry, I couldn't remember which time it was. Sorry, I'm sorry. Wrong. It's the video. So you watch the video. Yes, Caitlin.
It's supposed to say platypi on James.
Yeah, I looked, it didn't quite have platypi, it had platy, and I was like, I think I know what he's saying. And there shouldn't be 2 Y's, that's a mistake. But I did look up the plural because I was confused. I don't know why there's 2 Y's there, I just spelled that wrong.
You
It
put
did,
percent
2 Y's, but
So you get to pass.
Yes.
yeah, so you caught a misspelling there, Caitlin. So that'd be-
Wow.
So, and you get there's 1 brownie point. That's the first brownie point of the year. It goes to Caitlin. Yeah. Very good. So you still have an opportunity. I will say, Zendaya is here because she was like really popular in this group. I was kind of surprised. I'm like, all right,
All people. who watch
So-
the channel do.
Bailey, tell me about Virginia. Have you been or you want to go? You want to go. What part of Virginia?
Near Richmond.
Near Richmond. Is there something there you want to see?
Just the city.
Just want to see? Okay, because I'm a born and raised Virginia girl, so I can make recommendations for your travel. Piper, in Britain, where you've been or where you want to go?
Yeah.
Okay, and what do you want to do or where do you want to go specifically? Alex, hold on, go ahead.
Me?
Go ahead. You don't quite know, you just want to go in general. All right, very cool. Caitlin, I found your answer interesting. South Korea. So what is it about South Korea that makes you want to visit? Or did you visit? You don't know?
I just put a random thing.
Some say it has a lot of soul.
Yeah, there you go, a lot of soul. Ha, 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 Jack, oh my gosh, please, Piper, Jack. Jeez, that's a dad joke. Oh my gosh. So my dad is famous for jokes. So those of you who've been around a while, my dad had a stroke like a little over a year ago, and he had 2, and then it was really bad. But anyway, it was really, really bad. He almost died, but he likes to tell dad jokes. He always has like really just bad jokes that for a while he told jokes that made 0 sense. And he called you every day and told you some new joke and you just had to laugh, but the punchline it was completely disconnected. And you're like, eh. But we've got his medicines leveled up now and he's making good jokes again. He called me with one that made no sense the other day, but I was like, oh, okay. And I just laughed at it because he said something like, what does a door have in common with the door to a safe that you put money in? I'm like, I don't know. He said 10 feet and started laughing. I was like, what does that mean? And he's like, it's like 10 feet from the door. I was like, okay, like I guess you put your safe 10 feet. I don't know. So I just laughed. I was like, that's good, Dad. But then I called him on Sunday because I heard one. And I said, Dad, I have a joke for you. He's like, okay, because he was real excited because he loves to learn new ones. And I said, what do you call a deer with no eyes? And he said, I don't know, a blind deer. I said, no idea. He laughed and laughed. It was great. It was great. So,
Big joke in my family.
so I love dad jokes. You're good with them. Yeah.
I
I
didn't
know.
throw it in there. I just couldn't. It was right there.
Yeah. Yeah. Okay. There we go.
She said she didn't know. I said, well,
Does anybody else see anything super interesting on here you want to ask about? Like, what is that?
Jen put
And what is it?
too, that's why.
Why was Milo thinking about the structure of slugs?
Ah, yeah, that's interesting.
Why not?
Because he can.
Do you like slugs in particular?
No.
No. Not in particular, not particularly fond of this gastropod. No, it's not your,
Me and James both put Chris Hemsworth.
you know, they leave those little trails everywhere they go. And my best friend's dad used to take a Frisbee and he put beer in it. And he'd turn it, and then they'd go to the beer and try to drink the beer and they'd die. And that was his way of like attracting them away and killing them when he was having a picnic. Which was kind of weird. So the reason that works is, you ever seen people pour salt on slugs?
Yeah.
People used to do that when I was a kid all the time. If too many slugs, they would just pour salt on them all. And who can tell me why that works? Who remembers? James? Right, so the sodium goes, but sodium from the salt, sodium chloride.
Sure way.
Yeah, because there's trying to get this equilibrium, right, between the inside and outside, because we want, what's the word? Homeostasis, James, yes. So the salt goes into the slug because it's trying to get more salt on this side of the membrane, which in this case is the outside of the slug. And then the water inside the slug is trying to get out because it's trying to make a balance of the salt and water on both sides, and all the water coming out kills the slug. Yeah.
Piper, is the meat the character I'm thinking of from Face and Fur?
Yes.
Okay, I was like, that, I only know meat from Face and Fur, so it's either that or not. What a great.
All right, Alex, what you got?
Of course, it's either that or not that.
Well, it's like, I love Face and Fur, so I was
Why
thinking
are
of
you
meat from
saying
Face and
Also,
Fur.
I went to see drunk slugs.
Oh, they don't last long. They're not drunk for long. They just die.
Fish and Fur,
They're too drunk.
Yeah, why 20 goats in particular, Chloe? You don't know?
Number for me.
Ah, have you ever done like the goat yoga?
I feel like that's a reference.
No, I wanted to.
I want to do the goat yoga as well. I really do. It sounds like a great time.
You would.
There's
All right,
definitely a
so-
scene from a sitcom where it's like.
We have about 20-ish minutes left because you guys usually pack up. So here's what we're gonna do, because I'm gonna give you a minute to look over your homework answers, this page and then this page, and then we'll come back. But what we're gonna do after a couple minutes of looking at this is we're gonna go outside, and I have a beach ball, and the beach ball has questions all over it. And we're gonna toss it around in a circle. And when you catch it, whatever's closest to your right thumb is the question. You have to read out loud and then answer. And this is a good, some of them are science related questions and some of them are personal questions. So it's an icebreaker and a exercise all in one. Yeah,
Can I answer the one closer to my left thumb?
No.
instead?
right thumb. Yeah,
On a scale of 1 to 10, how personal are the questions?
not that personal.
All right, good.
Three.
3, I'd say 3. Yeah.
What do we do with Rico?
Ah, okay. What do we do with Rico? If you have drawn Rico, there are folders on the chest over there, and you make sure that your name is on the side that says name, not on the side where Rico is, and you slide it into the folder. Every week, that's what you can do with Rico if you've done it. Okay. So I'll give you a minute to look over this one. And when you guys think you've gotten it, got it mostly done, I'll give you a minute to look at the other one. And then we'll go outside and we'll kind of icebreaker meet each other, because there's a fair amount of new folks in here, and some of you know some of you, but not all of you. So give you a minute with this one, and then I'll flip to the other one. Oh boy. People are goofy.
Software is a little slow.
Huh. Oh, Liam, your mom messaged me asking if you should come in the front door, and I missed that because I was teaching. So guess you figured it out, huh?
Well, we did go to the wrong house earlier.
Where'd you go?
6-6-15.
Oh, I don't even know them. So,
That's fine.
I was some old guy.
yeah, I think he used to be on the what's it, architectural committee, the people that fuss about your lawn. Yeah, I think he used to be that guy. I don't know if he still is or not. All right, so give me a minute with this one. And then we will head outside for a few. Stretch about. Yes, James,
I have a question about.
Oops. About the what?
Why is there almost always a tree in front of the window?
in this neighborhood?
It really
Oh.
bothers her.
Why does it bother you? I don't know. I guess
You've been coming here for a year, now you just went to.
it's really interesting. I've never noticed that. Any window, just there's always a window. Ah.
It's almost always a tree in front of the.
That's a good point. I think the builders probably planted them and they just got big. Like in our case, it's pretty clear that they put in the cherry tree out front and the holly early on. But I know for a fact that they put in a crud ton of those crepe myrtles along the front of the house and probably around where the cherry tree is, because they whacked them all off, but those suckers sprout out of the bottom. They just keep coming up and it's maddening. They make little volunteers everywhere and they're not supposed to. Anybody else have a question about the lawns in my neighborhood?
That's really.
That was a really weird one. I mean,
My house, 'cause there is a lot of trees.
I never thought about that. Now, if you've been here before, you'll notice that the woods look different. We had, my neighbor really wants to see the river. So he's taken down a lot of trees, right? So he can sit on his deck now. He even put a little desk there. He sits out there with his laptop and does his work and looks at the
Man, is
river.
really like,
Mhm.
going to work.
And then he's got another deck down lower in the woods. But we had a lot of little scrub trees taken out, and then we had the canopy raised up to about 40 feet. So you can see the river now, and in the winter, you'll really be able to see it, which is pretty cool. So we will do in a couple weeks a rock hounding lab where we will go out into the woods down towards the river, and everybody's gonna be looking for their own rock. And that's kind of a fun one. Everybody's probably gonna find mostly the same kind of rocks because we're looking in the same place. But the hooch does move stuff. So mhm.
Will we get to keep the?
Of course you will. Of course you will. Okay, so I think we're probably good. So I'm gonna stop this. Now, I will tell you, we weren't necessarily planning for backyard people, so you've got to watch for dog poop. But we're gonna go to that corner down there and we should be good.
We're gonna sit in the corner and look sad.
We're gonna go out the back door here